Log on, tune in, find out. Another good idea from Cambridge.
Thank you, and thanks the organizers for giving me the opportunity to speak here. I will report on recent and ongoing work on moduli of plane sheaves supported on curves of low multiplicity. And the setup is as follows. I will consider semi-stable sheaves on the complex projective plane which have support of dimension 1. Now, as you know, the Euler characteristic of the twisted sheaf f of m is a polynomial expression in M of degree 1. And the leading coefficient here, R, is called the multiplicity of the sheaf. Chi is the Euler characteristic. The ratio is the slope of the sheaf. So briefly, what semi-stability means, let me recall. It means that the sheaf is pure. There are no subsheaves supported on points, and for any proper subsheaf, the slope is less or equal than the slope of f. Now, if we fix the multiplicity and Euler characteristic, you get a coarse moduli space which parameterizes the semi-stable sheaves, and which is fine precisely if R and chi are coprime. And it's known already from the work of Le Potier that these coarse moduli spaces are irreducible, projective, of dimension R squared plus 1, locally factorial, smooth at points given by stable sheaves. But I'd like to get a bit of more geometric information about these spaces and to say concretely what are the semi-stable sheaves that give points in these spaces, at least for small multiplicity. And I will concentrate on the cases multiplicity 4 that has appeared, and it's joint work with Drezé from Paris, multiplicity 5, which has been accepted, and multiplicity 6, it's ongoing. So far I have finished one of the moduli spaces of multiplicity 6. There are 3 more to go. Now, as you know, mapping a sheaf to its twist gives an isomorphism of moduli spaces, so you may a priori assume that chi goes from 1 to R. And you also have a duality isomorphism, which takes a sheaf to its dual defined this way, x1 of f and the canonical sheaf. So you only half of these values for chi are enough for our investigations. Now, let me tell you what we have found for these 2 moduli spaces which are isomorphic. We have found that MP24, 1 can be decomposed into 2 strata, an open stratum, which is described in the first row. In the left column, you have the cohomological conditions that are satisfied by sheaves in this stratum. In the middle column, it says that every sheaf in the open stratum has such a resolution. I'll tell you later what are the morphisms involved here, not all injective morphisms. And there is also a closed stratum given by these cohomological conditions. The stratum has codimension 2, and every sheaf there has this kind of resolution. The morphisms here are precisely the injective morphisms, such that their restriction to O-1 is represented by a matrix with linearly independent entries. Now, if you apply the duality isomorphism, you get the stratification for MP2 4,3. Now, this moduli space has 3 strata. The smallest stratum of codimension 3 consists, in fact, of precisely the twisted structure sheaves of quartic curves on P2. The middle stratum is locally closed, codimension 1, and the generic sheaves are precisely cokernels of injective morphisms from 2O- to 2O. Oh, I should have mentioned, I starting with multiplicity 4 because multiplicity 1 and 2 is trivial. Multiplicity 3 has already been done by Dreze. And finally, this moduli space again, I'm sorry, Le Potier, not Dreze. Le Potier knew that the generic sheaves have this kind of resolution in MP244, and he knew that this is the theta divisor here. It's a codimension 1 subvariety, and our contribution was to find out explicitly what are the shifts in the theta divisor. They are all shifts with this kind of resolutions. I'll tell you later what the morphisms involved are there. But before I give more details, I'd like to briefly go over the tools that I will use. So firstly, the Bilinson spectral sequence. As you know, for every sheaf on Pn, there is a spectral sequence defined like that, which converges to f in degree 0 and to 0 otherwise. Now, in my situation, sheaves on the plane with support of dimension 1, all I care about is this table. This is the E1 part of the spectral sequence, and this is the E2 part, and the sequence degenerates at E3. So you get a bunch of exact sequences involving the sheaf F, and they allow us to find the resolutions that I showed you. Okay, the other tool that I will use is the Bilinson free monad. Again, for every coherent sheaf on Pn, you have a monad with middle cohomology F, and these guys here are simply the terms in the total complex of the E1 term of the Bilinson spectral sequence. Okay, the other thing that I will use is the vanishing for semi-stable sheaves on P2 with support of dimension 1. So this is also was known to Le Potier. I'm not sure who first obtained this vanishing. Okay, so now let's give more details about, let me start with this moduli space, MP242. The first observation is that if a sheaf is, if the cohomology of a sheaf satisfies this property, then it must be the structure sheaf of a quartic twisted by tensor with O of 1. And the proof is going to be omitted. Next, I'd like to show that also I can concentrate on sheaves satisfying this cohomological condition, and I want to show that H1 is also 0. So I'm going to present a very simple-minded argument involving that gives a flavor of how the Bilinson monad and the Bilinson spectral sequence are used. And it's very easy to follow, but I don't want you to think that all our arguments are that simple-minded. So let's assume that, let's pretend that there is such a sheaf with H0 of f minus 1 is 0 and H1 positive. So I simply write the E1 term of the Bilinson spectral sequence. Since Phi2 is surjective, P is at least Q plus 2, and Q is positive. On the other hand, Phi4 is injective, so P is at most Q plus 2. So now I know P, and then I write the Bilinson monad. That's the Bilinson monad for the sheaf F, and the morphism from like terms from here to here is 0, so I get a commutative diagram like that, which produces a destabilizing subsheaf. And that's it. Contradiction. So now I can assume that all sheaves, I mean, I can restrict my attention to sheaves satisfying these two properties. And again, doing stuff with the Bilinson monad. And we get the possible resolutions that these sheaves can satisfy. Either this resolution in the case when H0 of f tensor to omega 1 of 1 is 0, or this resolution. The morphisms involved here are precisely the ones for which U1 and U2 are linearly independent, same for these two entries. Okay, so now if you know the resolutions, you can find the generic shifts in each stratum. They're here the generic shifts in the open stratum are of this form, where C is a smooth quartic. These are 4 points, no 3 of which are collinear. And the generic shifts in the closed stratum are of this form, in which 3 of these points are collinear. Before I go further, a brief discussion about Kronecker modules. Kronecker module is simply a matrix, an n by m matrix with entries in the V upper star, where V is a fixed finite dimensional vector space over C. And then you act from left and right by multiplication with invertible matrices. So this you projectivize, you look at take the special SLN times SLN, and you do geometric invariant theory, and you get some JT quotients here for the set of semi-stable matrices, which I denote like this, and a geometric quotient for the set of stable matrices. And of course they depend only on the dimension of V, so I can denote them like this. And they are called, I'm not sure why, but they are called moduli spaces of Kronecker modules. And there is quite a bit of information known about them, about these moduli spaces. They are smooth if M and N are coprime, and there is a universal morphism, which maybe I can skip. But back to the moduli space MP2 4,2. Let's look again at the space of homomorphisms from 2 minus 2 to 2O. We saw that injective homomorphisms have semi-stable cokernels, but there is also the open subset of morphisms that are semi-stable as Kronecker modules, and that set is larger than the set of injective morphisms. W0 here is the set of injective morphisms. WS is the set of semi-stable morphisms as Kronecker modules, and the guys that are semi-stable but are not injective have this form. I mean, this matrix here clearly has determinant 0, but if y1, y2 and are linearly independent and u1, u2 are linearly independent, then it is stable, in fact. So the stratum x sub 0 inside the moduli space, which is a good quotient of W0 modulo G0, is an open subset inside a good quotient, which is this Kronecker moduli space. In fact, it is the complement of the image of these matrices under the quotient map, which is a P2 times P2. So, so far we have that this Kronecker moduli space and our moduli space are birational, but we can get a bit more information about that in just a second. Before I say what I have on my mind, let me just mention that the stratum x1 is also a geometric quotient of the set of matrices of this kind here, modulo the group involved. Now, if I take the union of these two strata, the open and the locally closed one, I get an open subset inside my moduli space, which again is a quotient. And I get a canonical map from this open subset to the set of Kronecker, the moduli space of Kronecker morphisms, of semi-stable Kronecker morphisms, which I can explain how you get this map. First, you get a map from matrices of from this kind of morphisms to semi-stable morphisms by doing this operation, and then that map is invariant. It factors through little delta. Now it so happens that delta is an isomorphism over x0, and the preimage of P2 times P2 is of codimension 1. So it factors through the blow-up of the Kronecker moduli space along P2 times P2. And this blow-up map is an open immersion. It's in fact an isomorphism of the onto the complement of some P2, and this can be understood by looking at the fibers of delta over P2 times P2 embedded in the Kronecker moduli space. It turns out that away from the diagonal, the fibers are P12, but on the diagonal are P12 minus a point. So here is what we get so far. We get that we can obtain the moduli space by removing a P2 from the blow-up of the Kronecker moduli space along a P2 times P2, and then adding a projective space, the projective space of quartics. So for the picture is however not complete because I'm not sure how you glued this space here, how you glue it to that in order to obtain the moduli space. So that's something that's a future project. And now I have a section about quotient modulo non-reductive groups, which maybe I'll skip. Next, I'd like to talk about these two moduli spaces, which I told you they are isomorphic. And first, a proposition which I'm not going to prove. I assume that, let's assume that F satisfies this cohomological condition, then we get this kind of resolution again from the Beilinson monad, in which the restriction to phi of p to the second component is represented by a matrix having linearly independent maximal minors. This is precisely equivalent to saying that it's semi-stable as a Kronecker module. And again, I look at the I denote by x sub 0 the open stratum of such sheaves. Now, if I know what kind of form phi can have, then I can tell more. I can say more about the sheaves involved. They are either extensions of this form, in which C is a cubic, L is a line, or they are ideal sheaves of schemes of length 0 and of length 3 and degree 0, I mean dimension 0 inside quartic curves twisted tensorfully O of 2. Okay, again, I have my space of morphisms phi occurring here. Let me denote it W0, but I also have the semi-stable morphisms, which there is a way of defining semi-stability for this kind of morphisms, and modulo the group of the action of a group which is no longer reductive, automorphisms of this times automorphisms of this. But I can tell you concretely what semi-stability here means. It simply means that modulo the action of the group, my morphism cannot be of this form or of this form or of this form. And again, there are semi-stable matrices that are not injective. So what I get here is that my open stratum, which is the geometric quotient of W0 modulo G0, is a proper open subset inside the quotient of the space of semi-stable morphisms modulo G0, which has been described concretely by Dreze and Trautmann, this quotient. And let me explain heuristically how to construct the quotient. So you want to construct for morphisms that are not equivalent to anything like this, you want to construct a quotient. First, you restrict to 2O minus 2, and you take the quotient. That's a Kronecker moduli space, that one. Okay, then you have to account for the restriction of phi to O minus 2. So that's over a point, it's a vector space, a direct sum of 3 copies of S2V, where PV is the projective plane, modulo some subspace. So in any case, that gives you a vector bundle with base the Kronecker moduli space, which can be more rigorously constructed using the universal morphism on the Kronecker moduli space. And the quotient is the projectivization of the bundle. So what we found so far is that this space here, concretely constructed, is birational to my moduli space. Okay, so how about the closed stratum? Well, again, we can say precisely what are the shifts in there. They have resolutions of this form such that the restriction to O-1 has linearly independent entries. So they are ideal shifts of points on OC twisted by tensor field O of 1. And you can easily see that in this fashion you get the universal quartic. So the closed stratum is the universal quartic. Okay. Now to close the discussion about this moduli space, I have to prove that there are no other shifts involved besides the ones that I have already discussed. So actually I have to prove that H0 is 0 or 1. And here is how the proof goes. Let's take an arbitrary sheaf in the moduli space, write the Billienson monad for f of -1. It is this. So my moduli space is parameterized by an open subset inside the space of monads. And I can compute, of course, the tangent space at every point is given by this equation. Now I look at the map which takes A, B to B. Call it phi, that map. And the key is to show that phi has surjective differential at every point. Once you have shown that, let me do that later, but once you have shown that phi has surjective differential at every point, now you argue in this fashion. So you notice that the sheaves for which H1 is bigger or equal than 2 consists of the preimage under phi of matrices B that have rank at most 7. These matrices B are 9 by 10 matrices. Alright, so now every matrix of rank at most 7 is the limit of a sequence of matrices of rank 8, and he has surjective differential. Therefore, every sheaf that satisfies this cohomological condition is the limit of a sequence of sheaves for which H1 is 1. But the space of sheaves for which H1 is 1, I told you earlier, it's closed. It is the universal quartic. So there are no such sheaves satisfying this cohomological condition. And now how do you show the surjectivity of phi? You have to show that given beta, you can find alpha satisfying this relation. But that's sufficient. It's sufficient to show that the map alpha goes to B composed alpha is surjective. And for that you apply an X sequence, and you reduce to showing that H1 of kernel of B vanishes, but that follows from this exact sequence and from the fact that H1 of f of 1 vanishes. And that follows from the vanishing that I mentioned at the beginning of this talk. So I have done the same game, which is a bit more complicated for moduli spaces of multiplicity 5. So here is the summary. There are 3 moduli spaces of interest here. I'm sorry. So let's concentrate on this one. I found that this moduli space can be decomposed into 4 strata. An open dense stratum, 2 two locally closed strata of codimensions 2 and 3 and one closed stratum of codimension 5. In the second column you have the cohomological conditions that give you each stratum, and in the third column I'm telling you that every sheaf is the cokernel of some phi with precise description of what the morphisms phi involved are. So then you can get, knowing what are these phis here, you get concrete descriptions of the strata. The open stratum is a bundle over this Kronecker moduli space with fiber P14, etc. And the smallest stratum is the universal quintic. But again, the picture is incomplete because I don't know how the strata glue in order to give me the moduli space. Okay, so same story for this moduli space, and I should mention that in all situations except I guess for this situation, what happens is the stratum is the geometric or the good quotient of the space of morphisms modulo the groups detect naturally here, and the groups of course are, you see, in most cases they're non-reductive, but still the quotients can be constructed. Okay, so finally let me finish with showing you what I've done so far for multiplicity. The table was too big to fit into the Beamer template. So for multiplicity 6, the story is a bit more complicated. I look at this moduli space of sheaves having this Hilbert polynomial, PFM equals 6n plus 1. And then I get here a bunch of strata. However, one of the strata is not irreducible, is made of the union of these two guys, each of which is irreducible. So the picture is a bit more complicated. It gets more and more complicated, of course. I'm not sure how far I can go. Probably I can finish the multiplicity 6, describe completely what semi-stable sheaves are there. And further, I'm not sure about multiplicity 7, if this can be carried out. Thank you for your attention.
Is there any question?
I have a question. So there's a theorem by Gaeta on the syzygies of a generic ideal sheaf for points in the plane. I'm just wondering, is there an analogous theorem on an open? So for any R and chi, do you have is there an open stratum where the syzygies are particularly nice? And you have syzygies that only differ by at most 2, I think. That all your syzygies of the open stratum seem to all have the same kind of shape.
I'm not sure about that, but in some cases I can give quite generally, explicitly, what are the sheaves for, what are the generic sheaves. But I'm not sure about the syzygies.
Maybe time for another question. So if not, we meet again in 10 minutes at 2:40, and we thank Mario.